Mary. I'm presenting from Celestia. The title of my talk today is securing off-chain data availability for Ethereum L2s using Celestia. So a little bit of an agenda for today. And this talk is actually perfectly timed after the dank sharding talk, so you guys are already familiar with some of the concepts. So the first thing I want to do is start by addressing some of the core concepts of our building blocks today. So that's scalability and modularity. And then second, I want to start talking about Celestiums. Celestiums are Ethereum L2s that use Celestia for off-chain data availability. And then finally, I'll go into some other aspects of our ecosystem, including unique aspects and potential that our ecosystem empowers, aka sovereign rollups. So let's get started. So this is a screenshot that I took last night from both Etherscan, the Ethereum gas tracker, as well as L2 fees. So on the Ethereum gas tracker, you can see that gas fees, even in somewhat of a bear market, are still quite expensive. So you have an average of $2 per transaction, and for example, a OpenSea sale costs about $7 as of last night. People have attempted to scale this and lower transaction fees by batching together transactions into a single transaction called rollups. So you see the performance of rollups on the left side of the screen. So these costs range from 7 cents to about 46 cents. And that's still too expensive because rollups still require that transactions be processed on the Ethereum mainnet. And rollups still have scaling limitations of their own. So in the next bull run, when you see other deeds being minted for thousands of dollars again, you can expect that these transaction fees will rise as demand for Ethereum block space also increases. And this, of course, results in exponential gas fees. So here's a quote from Dankrad on a recent Ethereum forum post. Just like the base layer, the price of data for rollups will be volatile and based on demand. If there is a massive bull run or a big crisis, a lot more transactions tend to be made, and rollups will not be isolated from the high intensity of transactions. So rollups will have to be able to cope with volatility in any case. Next, our second core concept for today, modular blockchains. Modular blockchains decouple the core functions of the blockchain. So the core functions of the blockchain are execution, settlement, and data availability. Now, you can kind of see the progression of software from the monolithic era to the modular software era to finally the modular blockchain era. You can also think of this progression in the progression from Bitcoin to Ethereum to Celestia. So the Bitcoin network, enabled secure and anonymous peer-to-peer transactions designed to be a simple ledger of transactions. Ethereum was the first smart contracts platform that enabled programmable money that introduced more complex logic without the need for any intermediaries or counterparties. It's also the reason we're all here today. And then finally, Celestia. So Celestia was an innovative new concept in the idea of decoupling the core functions of any given blockchain. So instead of a monolithic blockchain performing all those functions and really kind of falling into the scalability trilemma of increased costs in return for increased security, Celestia decouples the blockchain so only focuses on data availability and consensus. Because it solely focuses on data availability, it's designed to be highly scalable and optimized for ordering data and making it available. Now, how does it work? So you see monolithic blockchains to your left. In monolithic blockchains, such as Ethereum full nodes have to download all the data in a block. To increase block space, you also have to increase hardware requirements. Modular blockchains, on the other hand, rely primarily on light nodes. Using light nodes, you only have to rely on multiple rounds of downloading smaller chunks of block data. So you can see a smaller chunk of block data being downloaded, and then because there's multiple rounds of verifying that the data is available and published, you increase and hit that confidence threshold that's predetermined. So you can receive a larger amount of block space in return for a minimal cost increase. We also have documentation on this. You can essentially run a Celestia light node from your smartphone. So here's a map of our validators as well as light nodes. You can see that it's truly decentralized, right? There's light nodes all over the planet, and the number of light nodes scales as the Celestia network increases in use as well. So the differences between light clients in monolithic blockchains as well as modular light nodes, like the Celestia light node. So in basic light clients simply verify that the majority of validators have approved a block. So they only check the header. So in that way, light clients are fairly unsecure. Modular light clients, on the other hand, both check the header and then also download a portion of that data. So if the data in that block is actually invalid, then it'll know. Thus, like Celestia light nodes have the same security, have similar security guarantees as monolithic blockchain full nodes. So now we get to Celestiums. Celestiums are an L2 chain that uses Celestia for data availability, but uses Ethereum for settlement and dispute resolution. For a handier visual, you can see the infrastructure stack behind me. So on the left-hand side, you see Celestiums relying on Ethereum for settlement and consensus, and using Celestia for data availability. Now, how does it work? So this is a high-level architecture of how Ethereum L2s can leverage Celestia for data availability. So Ethereum L2 operators post transaction data to Celestia's data availability layer. There it's placed by blocks. There it's placed into Celestia blocks by Celestia's proof-of-stake validators. Data is then relayed in the form of a data availability attestation from Celestia to Ethereum. The attestation is a Merkle root of the L2 data signed by Celestia validators, attesting to the fact that the data is in fact available on Celestia. Now, the DA bridge contract over here is a contract that sits on Ethereum. The DA bridge contract, called the quantum gravity bridge, is Celestia's data availability bridge contract that verifies the signatures of the DA attestation from Celestia. Now, when the L2 contract on Ethereum updates its state, it checks to make sure that the correct data was made available on Celestia by querying into the DA bridge contract instead of relying on transaction data being posted as call data to Ethereum, which is much more expensive and difficult to scale. Now, the bridge contract returns a positive response for any valid attestation that has been previously relayed to it, and negative if else. So here you can kind of think of a Celestium as a data availability committee with extra economic guarantees on data availability because the committee can be slashed if it misbehaves. This is possible because light nodes on Celestia's network can detect unavailable blocks with data availability sampling, which we've discussed previously. Because of data availability sampling, Celestia light nodes share the similar security guarantees of an Ethereum full node, and thus can automatically halt if the validator set becomes malicious. Celestia relies on Tendermint with proof of stake. So Celestia is a proof of stake Cosmos chain that relies on Tendermint and has a larger permissionless group of stakers on the network. Thus, once again, DA attestations that are incorrect and invalid can be penalized with slashing. So some comparisons with dank sharding, which you guys are all familiar with thanks to the presentation before. First in our comparison chart, we start with block times. block times are more or less negligible between a couple of different DA solutions. You see Celestia block times are approximately 15 seconds, and Ethereum with EIP 4844 are about 12 seconds. I'll focus in on EIP 4844. You can read the other two comparisons yourself as well. And then what matters more is kind of the time to finality. So between Ethereum and Celestia, the time to finality, even with 4844, is 12 minutes. So Ethereum's block production engine, titled Ghost, relies on probabilistic finality and uses Casper to provide faster finality. So even with faster finality, a faster guarantee of economic finality, the block time is still about 12 minutes. Celestia uses Tendermint for consensus, which has single slot finality. So once a block passes Celestia's consensus, it's finalized. Thus, the time to finality for Celestia is approximately 15 seconds. Next, data availability sampling. So Ethereum with EIP 4844, as the previous presentation mentioned, does not support data availability sampling and likely won't for the next 2 to 3 years. But Celestia does support data availability sampling. It's ready now. We're going to mainnet soon. So developers will be able to use Celestia's network, which has data availability sampling. To verify data availability on Ethereum, users must still run full nodes and download all of the data. So you see monolithic blockchains, as transaction number increases, so does the fees. And while cheaper with 4844, fees will still increase as well. But for modular blockchains, as mentioned previously before, as the number of light nodes increases in the network, the Celestia network scales with demand, so transaction fees stay fairly low. Now let's talk about light clients. So we've hit on this previously. Celestia light clients, Celestia light nodes rely on an honest minority because of data availability sampling. Light clients can't detect if an invalid block is produced by a dishonest majority of block producers because it relies on validators vouching for a block. Light nodes with data availability sampling get an upgrade in security because they can verify if invalid blocks are produced. So that this only happens if the DA layer focuses only on consensus and data availability. And then next, a little more on erasure coding and the encoding proof scheme. So erasure coding is an important mechanic that makes data availability sampling possible. This is because it extends a block by producing additional copies of the block data. This additional data creates redundancy and gives stronger security guarantees for the sampling process. Nodes still, however, may try to incorrectly encode data to disrupt the network. So you can see here, Ethereum with EIP 4844, EigenLayer, as well as Polygon Avail, all rely on a type of validity proof. So these kind of work in the same sense as validity proofs work in ZK rollups. So each time a block is produced, validators must produce commitments to the data, which nodes verify using a KZG proof. This proves that the block was encoded correctly. However, producing commitments for KZG proofs, producing Kate commitments for KZG proofs requires much more computational overhead, which means it increases the cost and increases the amount of hardware that's required. Generating commitments, however, doesn't carry as much overhead when blocks are small. As the blocks get larger, commitments for KZG proofs will carry a much higher burden to generate. Node types that are responsible for generating KZG commitments will require much higher hardware commitments. Celestia is unique because it uses a fraud scheme to detect incorrectly encoded blocks. Celestia nodes don't need to check if a block is correctly encoded. They assume it's correct by default. So the benefit is that block producers don't need to do expensive work to produce commitments for the erasure coding. And then finally, I'll talk about some other unique aspects of the Celestia network. So regarding sovereign rollups, developers can define themselves the execution and settlement layers, and then use Celestia for consensus and data availability. Now, what are some benefits of sovereign rollups? With sovereign rollups, you inherit that same scalability I discussed before. As demand for Celestia's block space increases, block space increases as well, and the light nodes increase alongside that. So, scalability is received through Celestia's data availability sampling technique. And then rollups that deploy in Celestia share security via Celestia's validator set. These rollups also maintain sovereignty because they define both the execution and the settlement layers themselves. So previously, when folks wanted to launch their own monolithic blockchain, right, we can think of a lot of different alternative layer ones. They had to build their own security from scratch. They had to build their own validator set. With modular blockchains, you inherit security from day one. So you can deploy your own rollup, define your own execution and settlement layers, and then inherit security through Celestia's decentralized validator set. So there's a lot of different configurations that allows for hyper customizability as well as versatility for the end developer. So developers can choose EVM, Solana virtual machine environments. You can choose to deploy a Move rollup. You can choose to either be part of a shared sequencer network or rely on a decentralized sequencer. The possibilities are kind of endless with Celestia. Right now, a number of rollups as a service projects are in the works and work with projects such as DeFi protocols and NFT projects to deploy rollups in a customized fashion. So I've included two links here, one to our build modular documentation, as well as another to the GitHub link for the quantum gravity bridge, which is the data availability bridge contract on Celestia. Please feel free to contact me either through Twitter or Telegram, and then please come find me if you have questions as well. Thank you.
Thank you, Mary, to bring this wonderful talk. So now we are open to 2 questions.
Hi, so thanks for the amazing talk. So I got one question. So how secure is the Celestia consensus network?
The consensus network is Tendermint. So Tendermint has never been hacked. It's the Tendermint BFT consensus.
Okay, so I assume it also depends on how many stakers in the network, right? Is it? Like, yeah.
How many stakers in the network?
Yeah, how many stakers in the, because the consensus depends on like the robustness of the stakers. If the stakers more, and that means that consensus algorithm will be more robust, right? Yeah, so I just want to ask, yeah, basically the security.
Yeah, so security increases, right, with the number of validators in the network. The network is still pre-launch, so right now we have 100 validators participating, and then post-launch, you know, we expect more validators to participate.
Okay, thank you.
Hello, Mary. Yeah, this is Will. Yeah, and I'm curious about why you put eigenlayer in the comparison table. Yeah, because I think like Celestia is a layer 1, and eigenlayer is something like a protocol. And so if you talk about the finality of eigenlayer, so it means it will be the same answer with Ethereum, because now they're building on Ethereum. So if today they're building on like Tendermint or Cosmos chain, the finality would be the performance of the Cosmos chain. So I'm just curious about that, and also give you some feedback about it.
Yeah, I mean, no, that's entirely correct. So eigenlayer is a set of smart contracts, right, on Ethereum. So it does share the same finality as Ethereum. We created that chart just because there are a lot of comparisons that we wanted to address because one of EigenLayer's products is EigenDA. So in that sense, it's just a comparison of data availability solutions.
Hi, Dijano from Risk Finance. I have two quick questions. One of them, like when you're taking the smaller blocks to do the validation on that, how are those blocks assigned? Are they assigned randomly? And if so, what pseudo-random number generator do you use for that? And then the other one, it was 15 seconds to get to final because of the assumption of the block being valid. But if there were to be a block that had a fraud in it, how long would the network take to react to detect that and pull the block? Or can you describe that one? Because I assume that would take extra time. Thank you.
Are you referring to like data withholding or? Like what, could you just restate?
Yeah, certainly. So it was 15 seconds for the block to be finalized. Mm-hmm. Now that is based on, it's faster because of the fraud-proof assumption, right? So there doesn't need to be fully validated because you're waiting for validators to come back with like a counterexample, maybe something like that. But how long does that take to happen? If there is a counterexample, that needs to be checked and validated, and then the slashing decisions need to be taken. And does that add extra time to the block processing time?
Yeah, that's a good question. I don't know the exact number of minutes time. I do know. Yeah, I can't recall off the top of my head right now. Sorry. I'll add me on Twitter or Telegram, and then I'll get back to you.
Okay, so if there are no questions, then we will finish our day one morning session. Our afternoon session will start at 1 p.m. So yeah, if you are interested in some of the talk, please come back to the building. And we provide a co-working space at the building B, which is on your right-hand side. And we also provide the booths, some of the booths, so you can go and visit if you are free after lunch. It's just close to our next building. Thank you.